Hey everyone. Today we're going to be talking about some group theory that's going to be necessary in order to derive quantum chromodynamics from local SU3 symmetry. So where should we start? Well, in the last video, we came up with this idea of a quark color triplet field. And we had this crazy thought about what if we can change what we mean by color different amounts at different points in space and time. And so we started to develop this image of what it would look like to do a local SU3 transformation on a color triplet field. So today, I wanted to explore the group theoretical framework surrounding SU3 so that we can really precisely articulate what exactly is a local SU3 transformation, and so we can start to lay out some of the ideas that are going to help us provide local SU3 symmetry into our model. All right, so let's go ahead and zoom in on a color triplet field, and we're going to go ahead and pluck out one triplet. Because to understand the triplet field, one must first understand the triplet itself. So, what even is a triplet, and how does it transform, and how can we describe what it means to do an SU3 transformation? Well, first, let's go back to basics and think about a single complex number. We'll call it psi. Well, now we can ask the question, what are all the ways that we can transform psi while keeping its magnitude constant? And by inspection, the only way to do that is to change the phase angle of the complex number by some arbitrary real-valued theta. And so we can write the transformed psi prime, is equal to e to the I theta times psi. And these are the U1 transformations that we know and love, that we've talked about in the electromagnetism video. But now I want to introduce some conceptual machinery that at first seems totally unnecessary and redundant, but will make a lot of sense in a moment. So what we're going to do is we're going to define a generator. We'll call it T0. So T0 is just the number 1. And so you might think, what's the point of that? The number 1 is already the number 1. We don't need to be giving it a special name. But check it out. We can think of T0 as being a kind of unit basis element in the real numbers, and then we can think of the phase angle of the transformation as being a multiple of that unit basis element. Now again, for U1, this is totally unnecessary. It's like we're putting more structure on it than we need, but this idea is going to scale up very nicely to higher dimensions. Because now we can write a U1 transformation as e to the I theta T0, and for higher dimensional unitary groups, we're going to have a very similar equation, but then instead of theta T0, we're going to have a sum over multiple real-valued theta parameters, each one of those thetas multiplied by one of these T generators. And you might wonder, why do we use the letter T for generator? Well, the way I remember it is T stands for the generator. All right, so now let's go to a slightly more interesting situation. Suppose we have a complex doublet, which you can think of as a vector in C2, the space of all two complex dimensional vectors. Now bear in mind, C2 actually has 4 degrees of freedom because each complex number has 2 degrees of freedom. So in this picture, I'm drawing the doublet as a blue and an orange complex number, and I'm using the colors blue and orange simply as a way to differentiate the two components. So the blue is the top component and the orange is the bottom component. Now you see this partially faded blue and orange that's stationary, and that represents the original doublet before we're transforming it, and then the solid blue and orange that are moving around, that's the transformed doublet, so that's going to be psi prime. And we could have started with any complex doublet. We didn't have to choose the one shown here where they're at right angles. I just picked that as an example. The main thing that this animation conveys is just giving you a sense of what it looks like for a doublet to be transformed while keeping its magnitude constant. Well, naturally, the question comes up, how exactly do we calculate the magnitude of a doublet? And the answer is, the magnitude squared of the doublet is calculated as psi dagger psi, where dagger is the transpose conjugate. So you flip psi horizontal, take the complex conjugate of its components, and then multiply that by psi. And when you evaluate that, you end up seeing that, okay, that's just the sum of the magnitude of psi 1 squared plus the magnitude of psi 2 squared. And so that's how you calculate the magnitude of a doublet. It's the square root of the sum of the magnitude squared of its complex components. So if we're holding the magnitude of psi constant, then these are called U2 transformations. And we can write that as the transformed doublet psi prime equals U times psi, where U is a 2x2 unitary matrix. And in a moment, we'll get into the definition of what exactly is a unitary matrix, what are its properties, what kind of matrix is it. But for now, all we have to know is that we can write U as e to the I theta a ta, where a is an index that runs from 0, 1, 2, 3, and we're summing over a. So theta a ta equals theta 0 t0 plus theta 1 t1 plus theta 2 t2 plus theta 3 t3. Now all of these theta values are real valued parameters. They're sort of like the phase angle of a U1 transformation. And then the t term, these are the generators of U2. Remember, t stands for the generators, and this time we have 4 of them. So the way to imagine this is that each generator gives us like a knob that we can turn, and the theta value is the amount that we're turning along that knob. A theta can be positive or negative, but it has to be real. Now these T generators, these comprise a basis in something called the Lie algebra of U2, and we'll get into that in just a moment. But for now, I'm just going to write out the most commonly used example of the generators of U2. So for T0, we can have 1/2 the identity matrix. Now this 1/2 is just a conventional scaling factor. Basically, you bake it into the definition of your generator so that you can avoid a factor of 2 later on. But the scale of the generators doesn't really matter, because when you think about it, when you're turning the knob with the theta angle, if you scale the definition of your generator up or down, all that does is it changes the scale of theta that gives you the same transformation. And with that in mind, you can see that really T0 is effectively just the identity matrix, which aligns really nicely with what we saw earlier, where T0 was just the number 1. But because now we're in 2 dimensions, we also have all these other options for what the generators can be. So for example, T1, we can use 1/2, 0, 1, 1, 0. For T2, we can use 1/2, 0, negative I, 0. And for T3, we can use 1/2, 1, 0, 0, negative 1. Now you might recognize these. The T1, T2, and T3 are just 1/2 of the famous Pauli matrices. And so the generators that I'm showing here, this is just the identity matrix, and then the 3 Pauli matrices, scaled by a factor of 1/2. So why are these matrices what we use for U2? Well, we'll get into that in more detail in just a moment, when we talk about UN and the Lie algebra of UN. But for now, let's recognize 2 things. First, all of these T matrices are equal to their own transpose conjugate. So if you transpose any of these matrices and take the complex conjugate of all the elements, you'll end up with the original matrix that you started with. So that is to say, all of these matrices are Hermitian. And the second thing to notice is that the generators T1, T2, and T3 all have 0 trace. The trace is the sum of the diagonal elements. And you can see with T1 and T2, the diagonal elements are just 0, 0, so 0 plus 0 is 0. And then for T3, the diagonal elements are 1, negative 1, which also adds up to 0. And then if you look at T0, you see 1, 1, so the trace of that is 2. Well, divided by 2, the trace is 1. So all that's to say, T0 is the generator that has the trace, and the other generators have no trace. And we find the same thing, by the way, when we scale up from a doublet to a triplet. Okay, so speaking of, I think it's finally triplet time. So the way to think about a triplet is it's just a doublet, but with 3 complex components instead of 2. And that's really all there is to it. But as we'll see, when you're messing around with triplets, things can actually get pretty complicated. And that's not just dating advice. And one of the things that makes it complicated is the number of generators. So for U1, we have 1 generator. For U2, we have 2 squared equals 4 generators. And for U3, we're going to have 3 squared, which is 9 generators. Now, much like the other 2 groups, our T0 generator is going to be proportional to the identity matrix, but then, of course, we're also going to have an octopus of other generators. I'll introduce you to the octopus later on. He's just stopping by for now to drop off our traceless Hermitian generators. Now these 8 traceless generators that the Octopus brought us, these are the famous Gell-Mann matrices, divided by a normalization factor of 1/2. You don't have to memorize the Gell-Mann matrices. I'll show them here. The only thing I want to point out about these is that they're sort of like the 3x3 version of the Pauli matrices, in that they're all traceless matrices, so the sum of their diagonal elements is 0, and also each one of these matrices is equal to its own transpose conjugate, so they're all Hermitian matrices. And we'll see later on why it's important for these matrices to have those properties. But for the time being, just think of the Gell-Mann matrices as the 3x3 version of the Pauli matrices. So in a moment, we're going to derive everything we need to know about how all of this math works. And if you're curious about how these calculations are done and how this animation was made, you can download the animation code on my Patreon. So for those of you who have signed up on there for $5 a month, first of all, thank you. Your support is what makes these videos possible. And for those of you who haven't signed up yet, but maybe are on the fence or considering it, well, if you sign up, then you can access this code that'll show you the behind-the-scenes math that goes into making this animation, which is actually also exactly the math we're talking about today, in terms of exponentiating generators into the unitary group and the Pauli matrices and the Gell-Mann matrices and all of that good stuff. So please consider joining the club if you haven't yet. All right, let's talk about complex vectors and complex matrices. And in particular, we'll focus on unitary transformations. And we'll figure out what is the special property of a matrix that makes it a unitary matrix. So imagine that psi is an n-dimensional complex valued vector. So we write that as psi is in Cn. So when n is 1, then psi is just a complex number. When n is 2, psi is a doublet. When n is 3, psi is a triplet, and so on and so on. And for our analysis, we're going to let n be some totally arbitrary natural number. So all of this reasoning is going to apply in arbitrarily high dimensions. And now let's say we have a matrix M, which is an n by n complex valued matrix. Now M is totally generic. We don't know anything about it. It can be whatever it can be. So it has 2n² degrees of freedom, because each of its n² complex components has 2 degrees of freedom. But now let's go ahead and define the matrix U, which is also a complex n by n dimensional matrix, but we're going to put a special property on this matrix U. We're going to insist that if we use U to transform our complex vector, that is, we're going to transform psi into psi prime, which is given by U times psi, then the matrix U has to be such that the magnitude of the transformed vector is the same as the magnitude of the original vector. And that right there is the essence of a unitary transformation. And so that's really all there is to it at the end of the day. Now the question comes up then, what kind of algebraic constraint does this unitary transformation put on the matrix U? What equation can we apply to the matrix U in order to ensure that it will transform our complex vector in a unitary way? Well, as we saw earlier, the magnitude squared of a complex vector is given by psi dagger psi, and all that is just psi star psi of each of the complex components within the complex vector. Now, when we're talking about this matrix U that lives in the space of n by n complex matrices, but also doesn't change the magnitude of the complex vector that it's transforming, we call those the unitary matrices. And they comprise the unitary group of degree n, which we write as Un. So we would say that our matrix U is in Un. By the way, later we're going to talk about the special unitary group Sun, and in that context, we're still going to say U is in Sun. So we have to be mindful. When you see U, that's just a matrix, typically a unitary or a special unitary matrix. Okay, but the question we're contending with now is what has to be true about our matrix U in order for the transformed complex vector U psi to have the same magnitude as the untransformed vector psi. Well, if you start with the equation shown here, that the magnitude of U psi equals the magnitude of psi, let's go ahead and square both sides of the equation. So we're comparing the magnitude squared to the magnitude squared. And as we know, the magnitude squared of a complex vector psi is psi dagger psi. So we have u psi dagger, u psi equals psi dagger psi. And that equation must be true if our matrix U is unitary. Okay, so now let's evaluate the transpose conjugate of u psi on the left side of the equation. When you apply the transpose conjugate to the product of two things, you end up getting the product of the transpose conjugate of those two things in reverse order. So AB dagger equals B dagger A dagger, and therefore U psi dagger equals psi dagger U dagger. So we end up with the equation shown here. And this is awesome because now if you look at both sides of this equation, you see that it's a psi dagger psi. But on the left side, we also have this expression U dagger U. And the only way that psi dagger U dagger U psi can equal psi dagger psi is if U dagger U equals the identity matrix, because then that term goes away because we're multiplying by 1, right? So you end up with just psi dagger psi. And that right there, my friends, is a beautiful and profound result. For we have just demonstrated that a matrix is unitary if and only if U dagger U equals I. And by the way, if U dagger U equals I, that also automatically implies that U dagger equals I, as well as the fact that U dagger, the transpose conjugate of U, is also equal to the inverse of U for a unitary matrix. Now, when you think about the nature of that constraint, you realize that it removes n squared degrees of freedom from the space of n by n complex-valued matrices. The reason being, U is an n by n matrix, so it has n rows and n columns. And in the equation U dagger U equals I, the left-hand side of that equation, you have U dagger U. Well, whatever U is, U dagger is automatically determined. So what you end up getting in this constraint is that the n rows of U dagger get dot producted with the n columns of U, and each of those dot products have to equal either a 0 or a 1 in the identity matrix. So imagine the identity matrix as containing n squared numbers, either a 1 if it's a diagonal element or a 0 elsewhere, and each of those 0s and 1s in I is what the dot product of the row of U dagger and the column of U have to be. So when you think about it like that, you realize that if you put your imagination in the 2n squared dimensional space of complex n by n matrices, and then you restrict your attention in that space to the unitary matrices, you're going to take out n squared degrees of freedom because of the unitarity constraint. And so the remaining space of unitary n by n matrices only has n squared dimensions. But the word space is a bit casual because there's actually some really interesting topological stuff going on with the unitary group UN. Because when you think about it, it's like imagine you're in the 2n squared dimensional space of complex n by n matrices. Imagine at the origin of that space, you have the zero matrix. And then far from the origin, you have matrices with huge numbers. So the unitary matrices are the ones that are neither too big nor too small. They don't grow and they don't shrink the vectors they act on. They transform them in a unitary way. And so the group of unitary matrices is actually like this compact manifold within the space of all n by n complex matrices. And we'll talk about that more later on when we get into the Lie algebra and the exponential map and all that good stuff. All right, now I want to show you a visual real quick that's just going to be a bit of foreshadowing. So we'll talk about this in more detail in just a moment, but I just want to put something in your imagination that's going to make what we're talking about later make more sense. All right, so you can think about the unitary transformations as the group of matrices that transform n-dimensional complex vectors without changing their magnitude. And corresponding to each of these unitary transformations, we have n-squared generators that, as the name suggests, generate the transformations in a way that we'll go into more detail on in a moment. Well, now the picture I want to put in your mind is that there's a special subgroup of the unitary transformations, known as the special unitary transformations, that you can get simply by turning off the T0 generator that's proportional to the identity matrix. So you ready for this? We're going to turn it off, okay? Ready? There we go. So now we're looking at special unitary transformations. In the generator picture, we've turned off the T0 generators. In the picture of the transforming complex vectors, we've removed a global phase-like degree of freedom. And as you see, that has a very dramatic effect on SU1, because there's nothing that can move, and so SU1 isn't really a thing at all. And then for SU2 and SU3 and SUN in general, it's a bit hard to see by looking at the transforming complex vectors, but when we turn off the T0 generator, we are removing a U1 phase-like degree of freedom that would otherwise change the phase of all components in the complex vector by the same amount. But we'll come back to that in just a moment. I just wanted to show you the picture for now. But before we can talk about that in more detail, we have to be a bit formal for a second and develop some terminology and some definitions. Okay, so we're talking about group theory today, so I figure it'd be helpful to go over some definitions. Maybe you've seen this before, maybe you haven't, but I figure it's good to take a moment just to make sure we're all on the same page. Alright, so first of all, in math, there's something called a set. And we use the word set in everyday life, but it's kind of hard to come up with a technical definition of what exactly a set is. So my favorite definition is, consider the set of all definitions of what a set is, pick the best one, and that's what a set is, okay? Kind of take that as a self-defining starting point. Now, a group is a set of things that is equipped with some binary operation. Now, binary operation, that sounds fancy, but that's just a way for two things in the set to intermingle with each other. So, for example, that operation might be multiplication, or addition, or matrix multiplication, or composition. There's really a whole lot of options for what the operation can be. So this is a very generic concept. For example, you can imagine the set of integers equipped with addition. That's a group. You can imagine the set of U1 elements, e to the I theta, equipped with complex multiplication. That's a group. So there's all kinds of groups. But in addition to being a set with a binary operation, to be a group, it has to follow 4 rules. So first, there has to be an identity element within the set. So let's call that E. Now the definition of the identity element is that whenever it intermingles with any other element via the binary operation, it has no effect on that element. So if you take the product of E and A, that equals the product of A and E, which just equals A, for any group element A in the group. Now here when I say product, I'm speaking generically. So if the operation is addition, then that would actually be the sum, you know what I mean? So for example, if our group is the set of integers equipped with addition, then the identity would be 0. Or if our group is the set of U1 elements equipped with complex multiplication, then our identity is the number 1. Second rule is that for every element in the group, there has to be an inverse. So for example, if you have some element A, then the inverse of A is going to annihilate with A, and the result is that boring old identity element. So the product of A and its inverse is equal to the product of the inverse of A, and that equals the identity element E. So for example, if we have the group of integers equipped with addition, the inverse of every element A is just going to be negative A, because A plus negative A equals 0. Likewise, if we consider the group of U1 elements, then the inverse of every element, e to the I theta, is going to be its complex conjugate, e to the negative I theta, because e to the I theta times e to the negative I theta equals 1. Alright, the third rule is that the group has to be closed. That is, that the elements of the group cannot conspire with each other to escape. So if A is in the group and B is in the group, then for sure, 100% guarantee, the product of A and B is going to be in the group. And so in that sense, there's no way out of the group. The group is closed. For example, again, if we take the integers under addition as our group, whenever you add up 2 integers, the result is always an integer. Likewise, if you're multiplying U1 elements, you always end up with another U1 element. As a counterexample of something that doesn't qualify as a group because it's not closed, consider the set of integers equipped with division. You can divide two integers, and the result is not always an integer. And so the integers equipped with division are not a group, because that doesn't have closure. All right, and finally, we also have the rule of associativity. And what that says is, suppose you take three group elements, A, B, and C, that are all in the group, and if you want to have the three of them intermingle, well, you have to do it two at a time, because the group operation is a binary operation, which by definition means it only acts on two things at a time. But it doesn't matter whether first A and B intermingle and then that intermingles with C, or if you have the product of A times the result of B and C intermingling together. So with these four rules, you can actually draw a lot of conclusions, and that's why group theory is so powerful, because it's so generic, and yet it has just enough structure that you can derive all kinds of really powerful results about all kinds of different groups. Now there's a fifth rule that's a bonus rule, and this is totally optional. A group doesn't have to have it. That is commutativity. If it's always true that the products of A and B equals the product of B and A for any two elements in the group, then we say that the group is abelian. That's a fancy word that just means everything commutes. But if there are any elements in the group that do not commute, so the order matters when you take the product of A and B, then we say the whole group is non-abelian. So it's still a group. It has met the four mandatory rules, but if it doesn't have commutativity, well, it's not an abelian group. So obviously abelian groups are very nice to work with because the math is a lot simpler. Non-abelian groups are more tricky because you just have to be more careful. So when we were dealing with electromagnetism, we had the gauge group U1, and that's an abelian group because it doesn't matter what order you multiply complex numbers. But when dealing with the strong force, we have the gauge group SU3, and in SU3 the order of multiplication does matter. So SU3 is a non-abelian group, and as a result, we say that quantum chromodynamics is a non-abelian gauge theory. A common theme that'll come up as we explore this math is that abelian gauge theory is just non-abelian gauge theory in the limit of no non. Okay? But at the end of the day, it's all just gauge theory. You know what I mean? All right, now a final bit of terminology. If the elements of a group comprise a continuous manifold, and the operation is smooth, we call that a Lie group. So a continuous manifold is just something that feels like a space. So, for example, if you have a circle is a continuous manifold. If you zoom in on a circle, zoom in real close, it looks like a line segment, and a line segment is a one-dimensional space. But a manifold can also generalize the concept of a space. For example, if you consider a Mobius strip, well, a Mobius strip, if you zoom in real close, it looks like a two-dimensional plane, right, which is a two-dimensional space. But if you zoom out, a Mobius strip has a topologically non-trivial structure. So it's not exactly right to describe a Mobius strip as a two-dimensional space. You know, it has more character to it. And so we call it a manifold. Manifold is like a really generic, space-like kind of thing. So for example, we've been talking about integers equipped with addition. Well, that is not a continuous manifold. The integers are like a perforated number line. It's a discrete set of things, it's not continuous. On the other hand, if you consider the group U1 of e to the I thetas, that is a continuous manifold, because U1 has the topology of a circle, and complex multiplication is going to smoothly and continuously rotate things around that circle. So U1 is a Lie group. In general, UN is a Lie group, as well as SUN. So in physics, we often talk about SU3 and SU2 and U1, and these are all Lie groups. And in fact, these are all compact Lie groups. So a compact Lie group is when the manifold is finite, and it sort of loops back in on itself. It's closed in the topological sense, as opposed to a manifold that goes off continuously in all kinds of directions or has like some weird boundary to it. A compact Lie group you can think of as like this nice continuous cluster of elements. So UN and SUN are all compact Lie groups. And the study of compact Lie groups is very important in physics, and particularly when you're dealing with gauge theory. All right, let's talk about something called a Lie algebra. Corresponding to every Lie group, there is something called a Lie algebra, which has to do with the tangent space of the Lie group at the identity element. Now that sounds very abstract, but if you've dealt with U1 and e to the I theta, then you already have some experience with the Lie algebra, perhaps without even realizing it. I want to show you the three-step process for how you calculate the Lie algebra of a group. And even if at first this seems like, why are we doing these three steps? What's so relevant about this? Why does it matter? Once we use the Lie algebra and we explore the exponential map, this will all make a lot more sense, and it'll contextualize what we've been talking about in terms of generators and the elements of the Lie group. So the three-step process for determining the Lie algebra is: step 1, you go to the identity element of the group. Step 2 is to determine the tangent space at the identity element, and in just a minute we'll go through how to do that. And then step 3, if you're doing physics, you want to go ahead and divide those tangent space elements by the imaginary unit I. And that's purely a conventional thing, so a mathematician usually stops at step 2. As we'll see, it really doesn't change the structure of these ideas, whether we divide the Lie algebra by I, so long as our convention is consistent. All right, so let's determine the Lie algebra of the unitary group UN. Well, step number 1. For UN, the identity element is just the identity matrix I, because I is in UN, that is, I dagger I equals I, and also I times U equals U times I equals U for every other matrix U in UN. So based on Rule 1 of our group theory definitions, we can recognize that the identity matrix serves as the identity of the unitary group. Now, step 2 is to determine the tangent space at the identity. So imagine that you're in the 2n squared dimensional space of all complex n by n dimensional matrices. And within that space, there's this compact n squared dimensional manifold of the unitary matrices. The identity matrix is one point on that manifold, and tangent to that point, there's going to be an n squared dimensional space of matrices. So for example, if we're in U1, we have a circle, and you can imagine the vertical line of imaginary numbers tangent to the number 1 in the complex plane. But in general, the tangent space consists of all the directions where a tiny step from the identity matrix to a very close nearby matrix I plus epsilon x keeps us in the unitary group to first order an epsilon. So the way to think about that matrix I plus epsilon x is some totally arbitrary n by n complex valued matrix. So think of that as defining like a direction in the space of matrices. And then epsilon is a scalar quantity that we're going to make vanishingly small. So as epsilon approaches 0, I plus epsilon x approaches I, but it's actually sticking out some tiny infinitesimal direction in the direction of the matrix X. You see how that's a way of kind of probing the space of matrices, going a little tiny infinitesimal bit away from the identity element in some arbitrary matrix direction X. And so the tangent constraint is that the directions in the tangent space are going to be those such that to first order an epsilon, the step length, the matrix will remain in the unitary group. And we know what it means for a matrix to be in the unitary group. It means that the transpose conjugate of the matrix times the matrix itself has to equal the identity element. So if we simply analyze this equation, we can calculate the kind of matrix that our direction matrix X has to be in order to be in the tangent space at the identity matrix. So if you evaluate the transpose conjugate of I plus epsilon x, what you end up with is I plus epsilon times the transpose conjugate of x. The reason being, the identity equals its own transpose conjugate, and epsilon is a scalar. So that whole transpose conjugate expression just boils down to taking the transpose conjugate of our direction matrix X. Well then, if you simply FOIL through this expression, multiply things out, you get the expression I plus epsilon x dagger plus epsilon x plus epsilon squared x squared equals I. And remember, that equation is the constraint that ensures that our matrix X lives in the tangent space of the UN manifold at the identity element I. Now, if we go ahead and look at both sides of this equation, we can see that we have an I on both sides. And so we can cancel those out using Hammurabi's first law. That's an old reference. Some of you might be too young to remember the Bronze Age. Well, if we look at what's left over, notice that we have an expression involving epsilon squared. Now, epsilon is an infinitesimal number that we're going to drive towards 0. And as we're doing that, it becomes vanishingly small. So epsilon squared is a small times a small, and a small times a small is a tiny. And so that term is going to vanish in a vanishingly vanishing way, so we can simply neglect it because it's second order in epsilon, and we're only concerned with first order in epsilon when we're calculating the tangent space. Well now, then what we have left over is that epsilon x dagger plus epsilon x equals 0. So at this point, we can simply divide by epsilon and scoot the x on over to the right side of the equation, and we end up with the constraint that the transpose conjugate of x equals negative x. Now, the transpose conjugate is often called the Hermitian conjugate, but I call it transpose conjugate because that's what it is. But anyway, this equation x dagger equals negative x, this is the defining characteristic of something known as an anti-Hermitian matrix. So a matrix is Hermitian if it equals its own transpose conjugate, and it's anti-Hermitian if it equals the negative of its own transpose conjugate. So a mathematician would stop here, and they would simply say, okay, the Lie algebra of UN is the set of all complex n by n matrices X such that X is anti-Hermitian. And the reason a mathematician would stop there is they would say, look, that's the tangent space at the identity, it's very nice, it's very clean, and if you exponentiate any anti-Hermitian matrix, you'll find that that gives you a unitary matrix. So any matrix X, which is anti-Hermitian, if you simply take e to the x, you'll get a unitary matrix. And that's the cool thing about a Lie algebra, is that it's like a generalization of e to the I theta. Now, the reason in the physics convention we divide out by a factor of I is because we don't like thinking in terms of e to the something. We like thinking in terms of e to the I something. Like, for example, a U1 element is e to the I theta. So a mathematician would say that the Lie algebra of U1 is I theta, that is a purely imaginary number line, which is like a vertical line that spans the tangent space at the identity of U1. But in physics, we say, no, divide out by a factor of I. The Lie algebra of U1 is simply the real numbers, theta. And then to map the Lie algebra to the Lie group, we take e to the I times the Lie algebra, and so we do e to the I theta. And the reason it's nice to do that in physics is because then you can talk in terms of the phase angle theta, and you don't have to talk in terms of like an imaginary phase angle. But anyway, as you can see, it really doesn't matter which convention we choose, just so long as we're consistent and careful with our definitions. So throughout the rest of this video series, we are going to be using the physicist's convention, where the Lie algebra is the tangent space at the identity divided by the imaginary unit. So what happens when you take the space of all anti-Hermitian matrices and divide by a factor of I? Well, let's find out. Suppose we define the matrix H to be some anti-Hermitian matrix X divided by I. Well, you know, dividing by I is the same thing as multiplying by negative I. So we find that H is equal to negative IX. So what happens if we take the transpose conjugate of H? Well, take the transpose conjugate of negative IX. When the dagger acts on the negative I, it's going to convert that to a positive I. And then when dagger acts on the x, it's going to convert that to x dagger. But what do we know about x dagger? Well, we know that it equals negative x, because x is an anti-Hermitian matrix. And what we end up with is that h dagger equals negative ix. But wait a minute, we already saw that h equals negative ix. So h dagger equals h. So when you take the transpose conjugate of the matrix H, it doesn't do anything. And that is a Hermitian matrix, which is secretly why we're calling it H. Okay, so what have we learned here? The space of all anti-Hermitian matrices is the same as the space of all Hermitian matrices up to a factor of I. So if you multiply or divide by I, you can turn a Hermitian matrix into an anti-Hermitian matrix, and vice versa. And so in the physics convention, we would say that the Lie algebra of UN is comprised of all the Hermitian n by n complex matrices. And along with that definition, we would then say that if you take e to the IH, then you get some unitary matrix. Now this is actually a pretty powerful result that we've just derived here. And if you think through each of the different dimensions for n, you'll see that this really explains everything. So like for example, take n equals 1. Well, the 1 by 1 matrices, those are just complex numbers, right? So what is a Hermitian complex number? Well, it's a complex number that equals its own transpose conjugate. You can't really transpose a 1 by 1 thing, but you can take the conjugate. And the only kind of complex number that equals its own complex conjugate is a real number. And so that's why we deal with real valued phase angles when we're talking about e to the I theta. Now, if you take n equals 2 and you think about U2, and you ask what is the space of all 2 by 2 complex valued Hermitian matrices, well, it turns out that space can be spanned by the 2 by 2 identity matrix as well as the 3 Pauli matrices. Because notice the identity and the Pauli matrices are all Hermitian matrices, and they're all orthogonal to each other. So you can think of those 4 matrices as sort of like 4 basis vectors that span the Lie algebra of U2. That is, that span the tangent space of the Lie group of U2 at the identity element. And then likewise, if you think about n equals 3, and you think about U3, well then the 9-dimensional space of the Lie algebra of U3 is going to be spanned by 9 orthogonal Hermitian matrices. The most commonly used basis set is the 3 by 3 identity matrix, along with the 8 Gell-Mann matrices. So you see how all of these concepts fit together across all these different dimensionalities, you know what I mean? All right, I want to take a moment to talk about the exponential map as it pertains to the Lie group UN and its Lie algebra. So the reason we care about the Lie algebra of UN is that every unitary matrix U can be written as an exponential involving a Hermitian matrix H. So we can always write U equals e to the IH. Now, as we talked about earlier, if you're talking to a mathematician, they might say, no, actually U equals e to the x for anti-Hermitian x. But this is exactly the same idea. The only difference is whether you want to put the I in the definition of your Lie algebra, or if you want to put the I in the definition of your exponential. Now, I suppose there might be other reasons to care about the Lie algebra, but they all go back to this fundamental connection between the Lie algebra and the Lie group involving exponentiation. Now, as we've talked about, the simplest case is when n equals 1, because U1 elements are just unit magnitude complex numbers, and the Lie algebra of U1 are just the real numbers, because the complex conjugate of a real number equals itself. And this concept is very familiar to us because we often write U1 elements as e to the I theta without even really thinking about it, right? Like when you're learning about complex numbers, you sort of take it for granted that you can write a complex phase angle as e to the I theta. That's kind of already baked into your intuition if you have some experience with this kind of math and physics. So the relationship between a Lie group and its Lie algebra is so close that in the case of U1, we don't even think about it. I mean, e to the I theta and the phase angle, these are like two sides of the same coin, you know, they're so closely related concepts. And because these concepts are so closely related, there are very subtle things relating to U1 that you might not have even realized. So for example, think about U1 and electromagnetism. Well, as we saw in the other video, the four components of the electromagnetic four potential, that is the gauge field A mu, are real scalars. In other words, you can say A mu lives in U1. Now, if all we knew was electromagnetism, we wouldn't necessarily know whether that's a coincidence or not, right? But, as we'll see in this video series, SU3 symmetry implies that our gauge field G mu is going to live in SU3, which is the Lie algebra of SU3. And that's why gluons are a thing. The 8 gluon fields have to do with the 8 dimensions of SU3. Now, we've been talking about the unitary groups, so we'll have to take a moment to talk about the special unitary groups, but these things are very closely related. And by the way, in general, in any gauge theory, the components of the gauge field are going to live in the Lie algebra of the gauge group. So the Lie algebra is a very powerful concept. It gives us a very generic way of thinking about things. Now that we've seen the unitary group, UN, let's talk about the special unitary group, SUN. So the special unitary group is pretty much exactly the same thing as the unitary group, but with the additional constraint that all the matrices in the group should have a determinant of 1. Now, when it comes to the unitary matrices, the constraint that U dagger U equals I actually already implies that the magnitude of the determinant equals 1. But the determinant of a unitary matrix could have a non-zero complex phase angle, and so this additional constraint that a special unitary matrix has a determinant of 1, another way to think about that is we're saying that the determinant of the matrix has no complex phase. It's a real number. So if you want to take the n by n unitary group, UN, and reduce that to the special unitary group, that involves shaving off a circular U1 degree of freedom. So the unitary matrices involve this global phase factor that we don't have in the special unitary matrices. Now, because UN is an n-squared dimensional manifold, SUN is going to be n² minus 1 dimensional. So, for example, SU3 is 3² minus 1, which is 9 minus 1, which is 8 dimensional. And because SUN is an n² minus 1 dimensional manifold, then so is its Lie algebra, which we call SUN, because that's going to be the tangent space of SUN at the identity element. So we saw earlier that the Lie algebra of UN is the space of all Hermitian complex n by n matrices. Well, when we impose the constraint on SUN that the determinant of the matrix equals 1, in the Lie algebra, that condition translates into the constraint that the Lie algebra elements should have no trace. That is, that the sum of all the diagonal elements in the SUN matrices should equal 0. So when you think about the special unitary group, SUN, the thing that makes it special is that the matrix has a determinant of 1. And when you think about the Lie algebra, SUN, the thing that makes the Lie algebra special is that the matrices are traceless. And these things, the determinant being 1 and the Lie algebra elements being traceless, are of course exactly the same constraint looked at from two different perspectives. So let's go ahead and establish that connection so you can see how exactly this determinant equals 1 condition in the Lie group becomes a traceless condition in the Lie algebra. So suppose that we have a special unitary matrix that we write as e to the IH, where H is a Hermitian matrix. And we know for sure that if H is a Hermitian matrix, then e to the IH is definitely going to be a unitary matrix. But if we write the equation that the determinant of that matrix should equal 1, then that equation is true if and only if e to the IH is a special unitary matrix. Right? Because that's the special condition, is that the determinant equals 1. Well, now we can rearrange this equation because we can say that the determinant of e to the IH equals e to the I times the trace of H. And that's just one of those mathematical facts, you know? If you take the determinant of e to the power of a matrix, then it turns out that's going to equal e to the power of the trace of that matrix. And if your matrix can be written as I times H, you can pull the constant I out front. And so, as we've written there, you can say that the determinant of e to the IH equals e to the I times the trace of H. And in order for that condition to be true, you have to ask yourself, e to the I times what equals 1? Well, the answer is 0. Now, if you want to be technical, the answer is 2 pi n, where n is an integer. But if you're thinking on that level, then you recognize the discrete difference between each of those values of n, and you realize that in order for things to be smooth and continuous, this constraint does indeed imply that the matrices in our Lie algebra should all have a trace of 0, because if we're doing a transformation and one matrix is traceless over here, there's no way to smoothly and continuously deform into a matrix that has a trace of 2 pi n for non-zero n, right? So maybe that's too much detail. But anyway, the point is that there's a logical connection between the determinant of the matrix in the Lie group equaling 1 and the trace of the matrix in the Lie algebra equaling 0. And that's why, to go from the Lie algebra of the unitary group to the Lie algebra of the special unitary group, all we have to do is turn off the T0 generator, because the T0 generator is the only one that has any trace. Right? It's the one that's proportional to the identity matrix. And all of the other generators we've been looking at, whether you're talking the Pauli matrices or the Gell-Mann matrices, those all have a trace of 0. So you start off in the Lie algebra of UN, pop out the identity generator, and what remains is n squared minus 1 generators that span the space of traceless Hermitian n by n matrices. And now would be a good time to do a little bit of foreshadowing about the next part of this video series, which is that because we're building quantum chromodynamics based on SU3 symmetry, we're going to end up having a gauge field which is a 4-vector field whose components live in SU3, the space of traceless 3x3 Hermitian matrices. And because we know that the Lie algebra of U3 has 9 dimensions, because in general the Lie algebra of UN has n squared dimensions, minus 1 dimension because we popped out the identity generator, and so that leaves us with an 8-dimensional space. And as we'll see in the next video, that is exactly why we have 8 gluon fields. You know, while we're here on the topic of Lie groups and Lie algebras and the exponential map, I want to take a moment to reflect on some of the details of how exactly a Lie algebra element gets exponentiated on up into a Lie group element. So as we've seen, the easiest way to write a U1 element is just e to the I theta for some real-valued phase angle theta. And more generally, a UN element is most easily written as e to the I theta ATA, where, as we've talked about before, the thetas are all real numbers, and the t's are the generators. And now we know that the generators can be thought of as a set of basis vectors that span the Lie algebra of UN. Now the reason that exponential formula works, the reason we can just sum over theta ATA, is because theta ATA, you can think about it as like a point in the space of the Lie algebra of UN. And the exponential map, you can think about as curling up the whole Lie algebra into the whole compact Lie group UN. Now, if you imagine that, if you imagine exponentiating the entire space of the Lie algebra all in one fell swoop, the mapping is going to be infinitely surjective, meaning that the Lie algebra, which extends off infinitely in all of its dimensions, is going to curl up over and over again infinitely many times, periodically, onto the compact manifold of UN. So this is the simplest example, when n equals 1, but for higher n, the gist of the concept is very much the same. The Lie algebra of UN you can think of as being isomorphic to Cartesian n-squared space, a space that extends infinitely along the directions of all of its generators. And the Lie group, UN, you can think of as being a compact manifold, that smooth continuous compact cluster of unitary matrices. And whenever you're applying the exponential map to convert the Lie algebra elements into Lie group elements, you can imagine that Lie algebra infinite space as getting all curled on up into the compact manifold of UN. Although in higher dimensions, it's very difficult to imagine. Actually, you can kind of imagine it for SU2. So basically, SU2 is a 3-dimensional Lie group. Its Lie algebra, SU2, is a 3-dimensional Lie algebra, which is like a 3-dimensional space. And when you exponentiate SU2 into SU2, you can imagine a 3-dimensional space that kind of gets all curled on up into a hypersphere. Now the animation shown here, I guess it turned out kind of cool, but the problem is, when you're trying to visualize a three-dimensional infinite space getting all curled up into a hypersphere, well, if you make it look like a cube, then you get some artifacts from the corners of the cube. And it's kind of hard to fit a hypersphere into 3 dimensions anyway, so, you have to use red and blue. And anyway, this isn't my proudest work, but I do think it serves a useful purpose as a metaphor of the Lie algebra, which is a space that extends infinitely in all kinds of directions, getting curled on up into a compact cluster of unitary matrices. So just keep that in mind as kind of like a vague analogy or metaphor for thinking about how Lie algebra elements get exponentiated into the corresponding Lie group elements. Okay, so let's go ahead and summarize the ideas that we've been talking about into this table. So we're going to think in terms of n equals 1, n equals 2, and n equals 3. For each of these possibilities for n, we've seen how we can derive a basis set for the Lie algebra of un, as shown here. When n equals 1, the Lie algebra of un can be spanned simply with the number 1, right? T0 equals 1, as we've seen. It's kind of unnecessarily complicated for the dimensionality, but it is what it is. And if we look at n equals 2, we see the more interesting situation, where our generators are given by the identity matrix, as well as the 3 Pauli matrices, as well as a conventional normalization factor of 1/2. And remember, those are a set of orthogonal, 2x2 complex-valued Hermitian matrices. And then if we look at n equals 3, our generators are given by the identity, as well as the Gell-Mann matrices, and typically one bakes in a factor of root 6 on the identity matrix, which is the square root of twice the dimension you're working within. And then on the Gell-Mann matrices, we're going to go ahead and bake in a factor of 1/2. And just as we saw with n equals 2, for n equals 3, these generators are all orthogonal and Hermitian. And in all of these cases, for n equals 1, n equals 2, n equals 3, and even beyond for higher n, you can always write a un element as e to the I theta a ta, where a is some list of real numbers, and t is the list of generators, and you're summing over the index a. Now when it comes to SU-n, the Lie algebra of SU-n, to get that, all we do is we take the Lie algebra of un, and we take out the identity generator, because that leaves behind only the traceless generators. So if we do that for SU1, we start with the Lie algebra of U1, which has the generator 1, we take out that generator, and then we realize, oh no, we have no generator left. So there is no basis for SU1, and likewise, there's no such thing as SU1. I mean, if you want to be really pedantic, you can say SU1 is the group of multiplying something by 1, but that's kind of trivial, okay? So that's why you never hear anyone talk about SU1. But for n equals 2, start off with the Lie algebra of U2, pop out the identity generator, and what you're left with are the Pauli matrices with the normalization factor of 1/2. And likewise, for n equals 3, start with our generators of the Lie algebra of U3, pop out the identity, and what you end up with is 1/2 of the Gell-Mann matrices. And then, of course, as we saw before, any matrix U in SUN can be written as e to the I theta a ta, where a is a list of real numbers that now goes from 1 to n squared minus 1, and the t's are the generators. Now, if you followed along with all of that, then you're in a great position to learn about SU3 and SU3. All right, let me introduce you to the SU3 octopus. So SU3 is the Lie algebra of SU3. It's an 8-dimensional space, and it's very easy to get lost in an 8-dimensional space. But if you're ever lost, just remember, you can always ask the octopus for directions. The octopus, with its 8 tentacles, is naturally adapted to the 8-dimensional habitat of SU3. So the way to imagine it is that there's an octopus that lives in SU3. It's very lazy, it never moves, its body is at the 0 matrix, which you can think about as the origin of the space, SU3, and all of its 8 tentacles are perpendicular to each other, so they each point in 8 orthogonal directions in SU3. And we can imagine labeling the 8 tentacles T1, T2, ... up to T8. Hey, maybe T stands for the tentacles. And of course, each one of these tentacles corresponds to a generator of SU3. So from the octopus's point of view, every matrix in SU3, I call it M, is just 8 real numbers. M1, M2, M8, where the M with the index is just how far to go along the direction of each tentacle in order to get to that matrix. Now these M numbers, they can be positive or negative, but they're purely real numbers. So what the octopus lets us do is we can trade a SU3 matrix for a list of 8 real numbers, M1, M8. So the matrix M is equal to M1 times T1 plus plus M8 times T8. And we often write that in the more compact form, where we can say that M equals MA times TA, where because the A index is repeated, then by the Einstein summation convention, we're summing over all of those A's. This concept of writing a SU3 matrix as a list of 8 real numbers is something that we'll use very often in quantum chromodynamics, because as we'll see in the next video, our gauge field is going to have SU3 matrix-valued components. And so another way to think about that is you actually have 8 real-valued gauge fields, and those are the 8 gluon fields. Likewise, in the fourth part of this video series, when we derive the field strength tensor, we're going to see that its components are also SU3 matrix-valued. And so another way to think about that is in QCD, you have 8 real-valued field strength tensors. So keep in mind this character of the SU3 octopus, because we'll very often write a SU3 matrix in terms of how far to go along each of the tentacles. All right, now I know this octopus thing isn't like the most technical way to present the material, so let's get a little more technical here. Well, as we've seen, SU3 is the space of all traceless Hermitian 3x3 matrices. And naturally, that space has 8 dimensions. So if you look at the matrices I've written here, by inspection, you can see that these are all traceless and Hermitian. They're also all mutually orthogonal in the sense that how far you go along one doesn't change how far you've gone along another. So because we have 8 orthogonal matrices that are all in SU3, we know that these are going to span SU3. And so that's why we can write any matrix M in SU3 as a linear combination of these generators with real-valued coefficients. All right, I want to say a few words about the topology of SU3. That is, what kind of a manifold are we dealing with here? You know, U1 is a circle, SU2 is a hypersphere. So what is SU3? Well, you might think it's an 8 torus, or perhaps a 5 sphere, but it's not. But if we review the reasons we might think it's an 8 torus, or we might think it's a 5 sphere, then we'll be able to see the kind of thing that it actually is. So first of all, if you think about the Lie algebra, SU3, it has 8 generators. And then when you think about the exponential map, that's going to curl SU3 into SU3, with all of those dimensions of SU3 wrapping inwards infinitely surjectively. You might think, okay, well, perhaps each of those is like an independent circular degree of freedom, and if you have 8 of them, then topologically, that would be an 8-dimensional torus. But it's not like that. When SU3 curls up into SU3, it's more complicated than that. There's a more topologically non-trivial thing going on than just an 8 torus. Okay, but why would we think that it might be a 5 sphere? Well, we know that SU3 transforms complex triplets without changing their magnitude, and the space of all constant magnitude complex triplets is a 5 sphere. The reason being, a complex triplet has 6 real degrees of freedom. And if you just write those degrees of freedom as A, B, C, D, E, F, then the constraint that the magnitude of the triplet should be constant gives us the equation that the sum of the squares of each of those degrees of freedom should be constant. And that is precisely the equation that defines the 5 sphere, which is the 5-dimensional locus of points in 6-dimensional space that are all equidistant from the origin. And so because the space of things that SU3 acts on is the 5 sphere, then we might be tempted to think that the topology of SU3 is a 5 sphere. But that's actually not the case, because one thing we know for sure is that SU3 is an 8-dimensional thing, but the 5-sphere is only 5-dimensional. So how does an 8-dimensional thing wrap around a 5-dimensional thing? It seems like we'll have 3 redundant degrees of freedom in SU3. And in fact, that's exactly right. There are 3 redundant degrees of freedom in SU3 relative to any particular complex triplet. But it's a different 3-dimensional subgroup depending on which triplet you're looking at. See, that's the complicated thing. So if you pick a particular triplet psi, that psi defines something known as the stabilizer subgroup of that particular triplet, which is a 3-dimensional subgroup of SU3 that's actually isomorphic to SU2. So if you pick a particular psi and apply any of the SU3 transformations that are in that subgroup, it'll leave that particular triplet completely unchanged. But that same stabilizer subgroup for that particular triplet, in general, does transform another triplet. And so if you imagine picking 2 random triplets within the 5-sphere, that is the space of all possible constant magnitude triplets, then in general, those 2 triplets are going to have different stabilizer subgroups, that is, different subgroups of SU3 that have no effect on that particular triplet. But then as you move around in the 5-sphere of different triplets, the stabilizer subgroup changes from one triplet to another, and it changes in a way that's topologically non-trivial. And so you see, there's actually a lot of complicated stuff going on here. But the way to think about SU3 is as a fiber bundle whose base space is the 5-sphere of all constant magnitude triplets, and the fibers that live on that base space are the SU2 stabilizer subgroups for each triplet on the 5-sphere. Now, this is a very difficult thing to imagine. And for getting into quantum chromodynamics, you don't have to have, total clarity on the topology of SU3. For starters, it's more important just to have the appropriate amount of fear, okay? Just be aware that SU3 is a complicated kind of fiber bundle situation, so that you're not tempted to make too simple of an assumption about the kind of topology that we're dealing with. Well, in any case, despite the confusing topology of SU3, we can still use it and work with it and get to know it using the tools of group theory. I mean, after all, it is a compact Lie group, and we know it's Lie algebra, and so even though we don't have a crystal clear picture on this higher dimensional fiber bundle situation, we can still go ahead and approach the subject matter using the tools of mathematical reasoning. All right, now one more thing I want to talk about before we go are the SU3 structure constants. When we're dealing with SU3 and SU3, we'll often come across terms involving the commutator of TA and TB. In other words, the commutator of 2 SU3 generators, which by definition is TA times TB minus TB times TA. And it tells us something about the structure of the way in which the group doesn't commute. Now, the first thing we should recognize is that if TA and TB are generators of SU3, then they're both Hermitian matrices in the physics convention. And so the commutator of TA and TB is anti-Hermitian. And you can prove that like so. First, take the transpose conjugate of the commutator of TA and TB. When you apply the transpose conjugate to the product of TA-TB as well as TB-TA, in both cases you switch the order of the matrices. And this is because AB dagger equals B dagger A dagger. So you switch the order of them like so, and then because TA and TB are both Hermitian matrices, they're both equal to their own transpose conjugate. And so the daggers then just simply go away. And then what we're left with is the commutator with the terms reversed. So we can go ahead and pull out a minus sign and switch those TAs and TBs back to the original order that they were in. And now what you find is that you end up with a negative commutator of TA-TB. So the fact that the commutator of TA and TB is equal to the negative of its transpose conjugate is what we mean when we say that the commutator of TA and TB is anti-Hermitian. Now, it's also the case that the commutator of TA and TB is traceless. In general, a commutator is traceless because the trace of the product of two matrices is the same regardless of the order that you take the product in. So the trace of TA TB is equal to the trace of TB TA, and because the commutator is just TA TB minus TB TA, the trace of the commutator is going to be the trace of TA TB minus the trace of TB TA. Those two things are equal, and so you end up getting a trace of 0 when you evaluate the trace of the commutator. So when you think about that, you realize that the commutator of TA and TB is a traceless anti-Hermitian matrix, and so it can be written as I times a SU3 matrix. Because a SU3 matrix is traceless and Hermitian, and a Hermitian matrix times I becomes anti-Hermitian. And because every SU3 matrix can be written as a linear combination of the basis elements of SU3, right? Remember the octopus? Then we know that we can write the commutator of TA and TB as the imaginary unit I times some real-valued linear combination of the basis elements, TC. So in this equation, f, a, b, c are a set of real-valued constants which are defined by the above equation. Because based on the reasoning that we just went through, we know that we have to be able to find some real numbers such that this is the case. And there should be 512 of these numbers, because we have 64 possible commutator expressions. Dividing out the factor of I, you can pull that commutator into SU3, and then for each of those 64 expressions, the octopus gives us 8 real-valued scalars of where that expression lives in SU3. Now, at first, it's a bit overwhelming to think, oh my gosh, we have 512 values of f, a, b, c, one for each possible combination of a, b, and c. But fortunately, almost all of those are 0. Only 54 of them are non-zero. And okay, but still, it's like 54, that's a lot. But fortunately, of those 54, there's a pattern to them. They're all either plus or minus 1, 1/2, or root 3 over 2. So it's not quite as complicated as it seems. But it is complicated enough that you don't have to memorize it, okay? When you're dealing with QCD, you want to have like a computer program that can give you these numbers given some A, B, and C input. Or just don't evaluate it, just leave your answer in terms of FABC. I have a code on my Patreon, f_abc.py, and that's just a function where you put in the numbers A, B, and C as input, and it outputs FABC. The purpose of these structure constants is that they give us a way to write a commutator of the generators of SU3 in terms of the generators of SU3. So it's a way of getting out of a commutator expression and simplifying that to a sum over SU3 generators. Now, I know that seems really abstract right now, but we'll see a specific example later on when we're dealing with the field strength tensor and the Lagrangian and the gluon-gluon interactions. And when we see that, I think this will make more sense. One thing you should know about these numbers is that they're antisymmetric, meaning that if you switch any two of the indices, then you pick up a minus sign. So FABC is equal to negative FBAC. That's true no matter which of the indices you switch around. And you know what? It might be easier if we go ahead and squish this from a 3-dimensional thing down to a 2-dimensional thing, because we can just take all the 8 C slices and plot them in 8 2-dimensional plots as shown here. That kind of gives you a better view of the numbers. But not that it really matters though, you know what I mean? Because the computer gives you the specific numbers, and in your mind, you just have to know that there are these numbers. So let the computer worry about all the technical details. But for you, it's more important to be able to orchestrate these equations and just be aware that these numbers exist and of how to use them. And we'll get into that later on. For today, I just want to show you that they exist. All right, so in summary, today we learned some group theory. In the next video, we're going to apply these concepts to derive the gauge field G mu. And that's going to clean up the mess that would otherwise be created when we transform psi into psi prime with an arbitrary SU3 valued matrix field. And as we'll see, the properties of the gauge field are going to blossom naturally from the group theory of SU3. For example, we'll find that the components of the gauge field live in SU3, which means that we can think of our SU3 matrix-valued gauge field as 8 real scalar-valued gauge fields, and those are the gluon fields. And then we'll see that each gluon field is very much like the photon field from electromagnetism, but they naturally interact with each other due to the non-abelian nature of SU3. And it's those gluon-gluon interactions that lead to color confinement. So I know today's video is very mathematical, very abstract, but as we'll see, these abstract ideas actually have very profound, very deep, fundamental physical consequences. So I hope you enjoyed this part of the video, and I'll see you in the next one. Hey, I want to say thank you to everyone who's been supporting the channel on Patreon. There's been a lot of people signing up lately, so welcome to the club, and thank you so much. And I also want to give a special thanks to Jack Serino and Andy Jones, who are supporting the channel at a very generous amount. So thank you guys so much for that. It really means a lot. Yo, I'm lost in SU3. Too many matrices around me.
If you're ever lost, my friend, just remember me.
Yo, it's the Octopus.
The octopus that lives in SU3. Ooh.
What up, man?
I'll point you in the right directions, tell you where to go.
Thanks.
Just 8 real numbers, that's all you need to know.
Alright.
Ooh, yeah.
This is delightfully absurd. You gotta make the metaphor stick.